Oh my god! I got the AP Chem test today. I'm screwed.
Unless I can know the answers.
She rides the night next to me.
So for this first one, we want to find the number of moles of chlorine gas, Cl2. So we are given 120 degrees Celsius, the volume, which is 25 liters, and the pressure, which is 0.4 atm. So with these things, we can use the equation PV equals nRT. Manipulating that to find moles, we do N equals PV over RT. Just plugging everything in, making sure we're using 0.08206 for R, which will be on the equation sheet if you're taking the test, and making sure that we are changing our temperature to Kelvin. So we're just adding 273 to 120 degrees Celsius. We get 0.310 moles of chlorine gas. So we basically just plugged in our pressure 0.4 for P, 25 liters for V, R, of course, 0.08206, and temperature, we just added 273 to 120, which gave us 393. Next question, how many grams of carbon disulfide CS2 are needed to react completely with Cl2? So we already have the number of moles of Cl2 gas, which we calculated in our last question to be 0.310 moles. So using the first thing we need to recognize with this question is that for every 1 mole of Cl2, there is only 1/3 moles of CS2 because Cl2 is 3 times the amount of CS2. So this means we need to use the ratio 1 to 3, and we multiply that by our number of moles of Cl2, and that gives us 0.103 moles of CS2. Now, this question is asking us to find the number of grams, or the mass of CS2. So for this, we need to multiply 0.103 moles and 76.2 grams per mole, which is approximately the molar mass of CS2, which you can find using the periodic table. This will then give us 7.85 grams of CS2. Next question. At 30 degrees, the reaction is thermodynamically favorable, but no reaction is observed to occur. However, at 120 degrees, the reaction occurs at an observable rate. Explain how the higher temperature affects the collisions between the reactant molecules so that the reaction occurs at an observable rate at 120 degrees Celsius. So this question is an explanation question. So we want to give an explanation that refers to the temperature basically gives the molecules more energy and causes collisions to occur more frequently. So writing this out, we can write something like So in our explanation, we basically just want to make sure that we mention that the temperature makes the collisions occur more frequently and with more energy, and therefore the reaction rate increases. Okay, so for our next question, we have a graph that shows a distribution for collision energies of reactant molecules at 120 degrees Celsius. Now, we have to draw a second curve of the graph that shows the distribution for the same collision energies of reactant molecules at 30 degrees. Well, basically, what we know about this question is that, of course, there will be a higher fraction of collisions with higher energy for 120 degrees. On this graph, energy of collisions is on the x-axis, so basically, if for 30 degrees molecules, since it's a lower temperature, we would want kind of the curve of the graph, the apex of the graph, to be before that of the 120 degrees, because it of course has more molecules with less energy. So the apex of the curve is going to be before that for the one shown. So now here we can see the 120 degrees curve that's drawn. And like I said, we're just going to draw the apex so that it is before that of the 120 degrees. So the graph is just shifted slightly left. And that'll be the 30 degrees Celsius molecules. And that basically just shows that they have less energy because the temperature is lower. Okay, so for our next question, we just have a question based on Lewis dot structure. So we have to draw the structure for S2Cl2. Now basically the best way to do this is first count up the electrons for each atom, which you'll see I'll do in the next clip. This just makes sure that we don't go over while maintaining octets around each atom. An important thing is the number of electrons for each atom will be the number of valence electrons, and that is just based on what group each atom is in. Okay, so now we know we're adding up 2 7s because chlorine has 7 valence electrons, and 2 6s because sulfur has 6 valence electrons. Now, the best way to do this is just start making single bonds between each atom and filling out their octets. Now, if we count up our bonds between each atom as 2 electrons, as they are a pair of electrons, and then the lone pairs as well, it should equal 26. Okay guys, so for our next question, we have, what is the approximate value of the ClSS bond angle in the S2Cl2 molecule? So this is just talking about the bond angle for this sulfur atom being the central atom. So based on our VSEPA theory, we know that this sulfur atom has 4 electron pairs in total, and 2 of them are lone pairs represented by these 2 lines. So this means that this one will be bent. That will be the shape's name, which we don't need to put, but it's just easier to think about the angle this way. And the angle will be 107 degrees, approximately, because you only need to, in the AP, you only need to estimate the angle within 10 degrees of the actual answer. So we can just put 107, because that's approximately what it will be. And then it just asks, if the 2 ClSS bond angles are not equal, include both angles. Well, this is just the other one, with this sulfur atom being the central atom, and we can tell that it's the same because it has 4 electron pairs in total, and 2 of them are lone pairs. For our next question, we have another experiment. So CCl4 can be also produced by reacting CHCl3 with Cl2, as represented by this equation. At the completion of the reaction, a chemist successfully separates the CCl4 from the HCl by cooling the mixture at 70 degrees Celsius, at which temperature the CCl4 condenses while the HCl remains in the gaseous state. So identify all types of intermolecular forces in HCl. So if HCl condenses, if HCl remains in the gaseous state and CCl4 condenses, this means that HCl probably has weaker forces than CCl4, but that doesn't really tell us much. What we can tell is that, like all molecules, HCl will have London dispersion forces. So HCl has London dispersion forces. And now, because hydrogen and chlorine have significantly different electronegativity values, hydrogen chloride will also have a dipole moment, which means that for brief periods of time, all the electrons will go from one atom to another, and they will all go to the chlorine ion in HCl, making the chlorine side of the compound negatively charged. So this means that HCl will also have dipole forces created by those dipole moments that create polar attractions between it and other HCl molecules for brief periods of time. Let it be known that this doesn't mean that it's polar, but it does mean that for brief periods of time it has some polarity. So next we have what can be inferred about the relative strengths of the intermolecular forces in CCl4 and HCl. Now, like I said before, because CCl4 condenses and HCl remains in its gaseous state after them both being gases, once the chemist cools the mixture, this means that CCl4 has stronger attractive forces because it turns into its solid state, which is what condenses mean, quicker than HCl. Well, HCl doesn't actually. So this means that, so if we're writing it out, we can say something like,
Makes me forget that I still need so much. Red, red wine. It's up to you.
so basically our explanation shows that because CCl4 has a higher freezing point, it condenses more easily when cooling the substance. It means that its molecules are more attracted to one another than HCl, and therefore it has stronger intermolecular forces.
Alright, so part E. Now, a student is studying a decomposition reaction that runs at 90 degrees Celsius. The student collects the data at a concentration of urea as a function of time, as shown by the table graph below. So we have this table, which sort of looks like a first order reaction, and we have the table with the corresponding values for the graph. Alright, so part E. The student proposes the rate law. Rate equals K and then the concentration of the molecule. Alright, so explain how the data supports the student's proposed rate law. Alright, so this rate law is a first order reaction. So we're gonna have to look at the data and look at the half-life of this data. Since the half-life is constant, so if we look from 0 to 5 hours, we can see that the half-life is constant from 0 to 5 hours, 5 to 10 hours, 15 to 20 hours. So this is a first order reaction. So, since
You got me running, going out of my mind. You got me thinking that I'm wasting my time. Don't bring me down. No, 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 no. Ooh. I'll tell you once more before I get off the floor. Don't bring me down.
alright. And that's part 1, so let's go to part 2 of part E. Alright, you usually propose a rate law and the student's results to determine the value of the rate constant K. Include units with your answer. So we can find the rate law by using, there's lots of equations to this, but the most easiest in this case, since it's a constant half-life reaction, first order reaction, has a constant half-life, we can just use the equation K, the rate constant, equals, this should be on your, this is right on here. It's right on your So whenever you're when you're taking the exam, should be some right here. Always look at this equation chart. Even if you don't know how to quite solve a problem, you can always look at this, and it will give you some help. All right, so K equals 0.693 over the half-life. So the half-life, in this case, is 10 hours. Every 10 hours, half of the concentration disappears. All right, so all we have to do is put that equals 0.693 divided by 10 hours. And that equals simply 0.0693 hours. Remember, we have to put to the -1. So let's get our, because the 10 hours when we're solving the equation is in the denominator. Alright, so part F. The student learns that the decomposition reaction was run in a solution with a pH of 13. Briefly describe an experiment, including the initial conditions that you would change and the data you would gather, to determine whether the rate of the reaction depends on the concentration of hydroxide, OH. Alright, so all you have to do in this question is come up with your own experiment. Now we know that the pH should be, to find the pH of 13, we have to set the pH to a known value. And we also have to set the concentration to a known value. If we set these two constants to a known value of the CONH2, then we can find whether the rate of the reaction depends on the concentration of the hydroxide. Alright, so if we set the concentration and the pH equal to a known value, we can measure the rate of the decomposition by monitoring the concentration.
In the right sun shows just 1,000 reflections of my own sweet self, self.
For question 3 of the 2017 AP Chem free response. Alright, so this is right in the middle of the exam. We're getting tired, and now we're going to do question 3. So we have this reaction to start with. N2 plus O2 equals 2NO. So this already looks like the entropy is decreasing. We can make that assumption. At high temperatures, N2 and O2 can react to produce nitrogen monoxide, NO, as represented by the equation above. Alright, part A. Write an expression for an equilibrium constant, Kp, for the following forward reaction. Okay, so these are easy points on the test. These are pretty simple. Just always remember reactants over products, and the coefficients you write as exponents. So the Kp for this reaction, sorry, this is capital, is simply the products over the reactants. So NO, because there's a coefficient of 2, it's squared, all divided by N2 times O2. Alright, so that's your Kp. It'll look better on paper, but that's your Kp reaction. That's your Kp equilibrium expression for the forward reaction. Alright, so part B. A student injects N2 and O2 into a previously evacuated rigid vessel and raises the temperature to the vessel of 2000 degrees Celsius. At this temperature, the initial partial pressures of N2 and O2 are 6.01 atm. atmospheres and 1.61 atmospheres, respectively. The system is allowed to reach equilibrium. The partial pressure of NO at the equilibrium of 0.122 atmospheres. Calculate the value of Kp. So what we're basically doing is we're changing some of these conditions here. So we have to write an ice diagram. We have to make an ice diagram to solve this problem. All right. So let's create a table that's, let's say, about 5. Let's go that large, and let us write ice. So then label our headings according to the reaction. And then 2 and 2. All right. And then we have to just simply put all the partial pressures into the ice diagram. For the initial change, so first one is 6.01, second one is 1.61, and then it becomes, this is just simply 0 because we haven't, that's what we're trying to, then we put just 2x, negative x, and then, as we always do, 6.01 minus x, we simply just take the partial pressures and subtract them, 1.61 minus x, and this is just simply 2x. Since the, no, this is simply just 2x, which actually just, since the NO equals, the partial pressure of NO equals 1.122 atm, we can just set this equal to 0.122 atm. Alright, and now we just have to use the equation like we did in part A, the equilibrium constant expression. We just had to find x. So, and then finally get the equilibrium Kp. So, to find x, all we have to do is take this right here, divide that by 2. So if we divide by that by 2, x equals around 0.061. So then we put that in the equilibrium expression. So Kp equals, since the product's NO is 0.112, we just put 0.112 for that. 0.112, no, 0.2122, sorry. And divide that by the x values. We use these always. And that 61 minus 0.061. And then all of this equals 1.62 times 10 to the negative 3. Alright? A student is asked to make a buffer solution with a pH of 3.4 by using a 0.1 molar HNO2 and 0.1 molar NaOH. So, first let's write out the equation, the chemical equation for this this acid-base reaction. All right. So let's write the net ion equation. So we have the OH and the NaOH plus, let's write that negative, make that negative. Plus the HNO2 to make that. Yeah. And then use this arrow to represent. That creates NO2. Remember, we have to write acid-base reaction, net ionic reaction. So then, the acid is the hydrogen donator, and the NOH would be the acceptor in this case. So the HNO2 is the acid, and then the NaOH is the base in the forward reaction. So that would be a negative. And then plus, this simply just makes H2O. Alright, so now that we have the equation, we can solve part 1 and 2. Explain why the addition of a 0.1 NOH to another 0.1 molar HNO2 can result in the formation of a buffer solution. Include the net ionic equation for the reaction that occurs when the student adds NOH to the HNO2. So we know that the NOH is the limiting reactant. Okay? So the weak acid will only be partially neutralized by the base because it's a limiting reactant. Therefore, the products will only be half used or only partially used. So we'll have so when the reactants react, we'll only have a weak acid, basically like a half weak acid and a half conjugate base. So we'll have similar amounts. So that creates a buffer solution where there's no really large change in pH because you have the conjugate base and the weak acid. So let's write this down. Since the NaOH is a limiting reactant, Alright, so part 2. Determine the volume in milliliters of the 0.1 NaOH the student should add to the 100 milliliters of 0.1 HNO2 to make a buffer solution, the buffer solution that we have in part 1, with a pH of 3.4. Justify your answer. Remember to justify your answer in these. Whenever, read carefully on the AP exam. So we have a pH of 3.4. At a pH of 3.4, that is the halfway point between. You have to notice that that's the halfway point of the equivalence point. So it's the halfway of the halfway point, if you think of it that way. So that means the weak in the halfway to the equivalence point, the weak acid and the weak base, or the acid and the base, have to be equal. So all we have to do, this is simple stoichiometry. So we only have. So to make this, to determine the volume in milliliters of the NaOH we should add, all we have to do is, we know that we only have to add 50 milliliters of the 0.1 NaOH. And to the 100 milliliters HNO2. Now,
Okay, so now let's move on to question 4. So I'll let you read. I'll give you a bit of time to read the introduction and the look at the diagram. Okay, so now let's move on to question 4a. So 4a asks us which die A, B, or C is the least polar, and we need to justify our answer in terms of the interactions between the dyes and the solvent, or between the dyes and the paper. So, so if we look at the diagram now, on the left we can see that all the dyes start at the same point. Then if we flick to the right, once the chromatograms have been developed, we can see which ones have advanced more than the others, and we can clearly see that in diagram, in the one on the right, that dye C has traveled the furthest, which is and so that indicates to us that dye C is not attracted to the polar paper as much as the others are, which means it is least polar. And again, our explanation for that is because it travels the biggest distance compared to the other dyes from the origin. So if we write our answer now, we can say that the dye C, because it is not attracted to the polar paper as much as the others, because you can see that it travels the biggest distance compared to the other dyes from the origin. Part A. Now let's move on to part B, which the question asks, which dye is present in the unknown sample? So the first step here is trying to align kind of what the unknown sample is of one of the known dyes. And we can also see that the solvent front is different on both sides. So if this were stretched just a bit more to level off to that level, what would that dye line up with? Well, it definitely won't be dye B, because it would have to move up, and the shift wouldn't be big enough to go all the way to dye C. So the answer would have to be dye A, because the RF value is defined as the distance moved by the solute in comparison to the distance moved by the solvent. So you can see that the dye A, because the RF value for A in the known sample is the same as the RF value in the unknown sample, which is why that is our answer. So dye A, because the ratio of the distance moved by the solute in comparison to the distance moved by the solvent is equal to that ratio. You know, I would normally write that whole thing, this whole ratio distance moved, that, but let's just say I'm just going to shorten it to ratio to not waste time. So to that ratio for the unknown sample. And there we go. Let's move on to question 5. So I recommend you pause the video now and read the introduction, give these questions a try, and resume the video again. So I assume you've paused the video and you've given it a go. So now let's move on to question part A, which asks us, calculate the magnitude of the heat energy in kilojoules absorbed by the water. Assume that the energy released from the combustion is completely transferred to the water. So an equation should spring to mind as soon as we hear this, and this is the famous equation Q equals MC delta T, and so Q obviously being the heat energy. So now we look at all the different variables in that equation. So what is M? Do they give us M? Yes, they do. Here it is. The mass of the water is right there. So it's 125. We know it's 125 for M. They give us C, which is the specific heat capacity of water. They do. It's right here, 4.18. And do they give us delta T? Now they do not give us delta T itself, but they do give us temperatures after and before. And as you know, the delta in front means the change in temperature. So, and that will be equal to the final temperature minus the initial temperature, or the difference between both temperatures. So when resolving that, we find that, there we go. So that's the equation we find. And as a final answer, and let's not forget the units in joules. So that's our answer. But what are they asking the question? Kilojoules. And as we know, 1 kilojoule is 1,000 joules, so this is easy to convert afterwards. This gives us simply 15.2 kilojoules. So now let's move on to part B. So part B asks us, so I'll just read together. So part B asks us, based on the experimental data, if 1 mole of C3H7OH is combusted, how much heat in kilojoules is released? And report answer with the correct number of significant figures, which we'll have to take account of. So, first of all, when we see this in terms of moles, and we look at C3H7OH, we should be thinking about maybe calculating the molar mass or calculating the moles. And to calculate the moles, specific moles of C3H7OH, with the amount of mass they give us here, we probably need to figure out the molar mass. So let's do that first. Let's figure out the molar mass. So, the molar mass of C3H7OH. So how will we do that? So we would use our periodic table. So grab it if you have it there, and tell me the atomic mass of carbon. Yes, it's 12. And we know there's 3 of them, so we would multiply 12 by 3, and then add that up to H, was an atomic number of 1, and since there's 8 of them, that'd be 8 times 1, which is 8. So we would add 12 times 3, and then add that to 8, and add that to the atomic mass of O, which we know is 16. And so here it is here, just to show it to you. This is what our calculation would look like. So it's just simple addition, adding all the atomic masses up, and this will give us an answer of 60. So now next we would try and find the moles, and this is super simple. This is the base equation, which I think pretty much all of you would know. Moles equals mass over molar mass. Now, do we have the mass and molar mass? Yes, we have the molar mass. We've just calculated it here. We just did it. And do we have the mass? Yes, it's right here. They give it to us. Mass of C3H7OH combusted, which is what the question talks about. So what this would be, so here we go. So that's the equation. It's an infinite number, so we're just going to keep it in fractional form for now, which makes it a bit simpler. So now we're trying to find, now that we have the moles, and we've just calculated here the heat released during this reaction. Now all we have to do is divide one by the other. So we divide. Let's convert it to joules first. So we divide this is converted from this. These are both equal. So to find the amount of joules released in 1 mole, you divide the heat released by the amount of moles. And so this then gives us 1,661 joules per mole, which would give us here, in kilojoules per mole, 1.66. But they told us to take into consideration the significant figures. And if you can see, the information we've been given has been, here it's to 1 sig fig, here it's to 2. So it is best to use 2 sig figs in this occasion, and the final answer would therefore be 1.7 kilojoules per mole. Now let's look to question C. So as we can see, probably just looking at it, we probably understand that there's a bit more explanation in this one. So let's read the question. So a second student performs the experiment using the same mass of water at the same initial temperature. However, the student uses an alcohol burner containing CH3H7OH that is contaminated with water, which is miscible with C3H7OH. The difference in mass of the alcohol burner before and after the combustion in this experiment is also 0.55 grams. Would the final temperature of the water in the beaker heated by the alcohol burner in this experiment be greater than, less than, or equal to the final temperature of the water in the beaker in the first student's experiment? Justify our answer. So, before giving you any answers, I'm just gonna go through it logically with you guys. So, we can see that, first of all, we can see that they both have the same mass, but one of them is contaminated with water, which means that the one contaminated with water, for it to have the same mass as the one which is not contaminated and contains 100% of C3H7OH, that must mean that the mass in the contaminated one of C3H7OH has to be smaller, logically. So since there is less C3H7OH in the contaminated burner, this must result in less alcohol being burnt in the actual reaction compared to the one which is. Now just check. This is the answer I would have given. And yeah, that is it. That's all you need to say. Well, now let's move on to question 6. So I'll give you a bit of time to pause the video and read the instructions, and then maybe try it yourself, and then come back to the video. So I presume you've paused the video and given it a go. So now let's read question A, or part A rather, which asks us to calculate the number of grams of MgOH2, which has a molar mass of 58.32 grams per mole, that is dissolved in 100 milliliters of a saturated solution of MgOH2 at 25 degrees. So now this is relatively straightforward. So now we need to kind of, since they give us KSP, our first inclination is to kind of find the equation, the KSP equation. So what would that be? I don't know if you figured it out, but that would be the concentration of Mg2 plus multiplied by the concentration of OH minus squared. And because the equation for KSP is product over reactants, but since the reactants is MgOH2, which is a solid, this is not included in the KSP equation. So we end up with just simply the equation I just stated, Mg2 plus times OH minus squared. So now that's quite tricky actually. It's difficult to understand in terms of, now we could actually replace Mg2 plus and OH minus, Mg2 plus, with C. So the concentration of Mg2 plus, if we were substituting for C, then the concentration of OH minus would be 2C, because as we can see in this equation, there are twice as many OHs as Mg. So this is in terms of the ratio, and that squared still stays there. So if we do it here, we can see that that's what it gives us by just substituting in the C, and this is due to the ratio, I remind you. And let's keep going. So this is equal to 4C cubed, and then they give us the value of KSP. They give it to us. It's given here in the instruction, in the introduction here. So that's relatively simple. You just solve for C, and then you've got your concentration of Mg2 plus. So this would be how you solve it. It's a simple algebraic solution. So to isolate C, you have to divide the 4, bring the 4 this side by dividing by 4 on both sides, and then you cube root both sides to give you C cube root of this whole term here. It's not that term down there. And this cube root extends all the way. I know that here it's just very short, but it should normally extend all the way. So then it gives us a simple answer. Sorry, and of C, which is equal to 1.65 times 10 to the minus 4 moles per liter, or molarity. But the instruction does not ask us to find the number of moles in a liter. It asks us to find the number of moles in in 100. And as we know, 1 liter is 1,000 milliliters, and so 100 milliliters would be equal to 0.1 liters. So in 100 milliliters, 0.1 liters. And so then we would need to find the number of moles in 100 milliliters, and how we do that? Simply multiply by 0.1, which would give us this, 200 milliliters. So this is the unit. It may seem a bit strange, but that's what it is. And we only really need to know this bit now that we know the number of moles and that quantity. So if we move on now, we know this equation here. So the moles, which we have the moles, they're right here. We need to find the mass, which is what they're asking us. We have the molar mass, it's given to us here. But that equation is not helpful, so we rearrange it. We rearrange it in terms of the mass, and then it's very simple. And from then on out, extremely simple. We have both these values, and we go here. Sorry, this should be 5.32, and then our final answer is 9.6 times 10 to the minus 4 to 2 sig figs. Okay, so now let's move on to question 6. B, part B. So I suppose you've already given it a go. So let's read the question. So the energy required to separate the ions in the MgOH2 crystal lattice into individual Mg2+ and OH- ions, as represented in the table below, is known as the lattice energy of MgOH2. As shown in the table, the lattice energy of SrOH2 is less than the lattice energy of MgOH2. Explain why in terms of the periodic properties and Coulomb's law. So the first thing we would look at in terms of Coulomb's law is distances and the radii and charge density maybe. So let's first look at the periodic table quickly. So we can see that we're comparing Mg and Sr. So if we look, they are both 2+ ions, but Mg is a smaller ion than Mg2+, sorry, is a smaller ion than Sr2+. This means it is more charge dense, because in a smaller ion there is the same charge as another ion which has a bigger volume, resulting in more charge density in the Mg2+. So since it's more charge dense, then we can relate it to Coulomb's law, because Coulomb's law indicates that the closer the ions are to each other, the stronger the attractions. And since Mg is a smaller ion than Sr, Mg2+ is smaller than Sr2+, that results in a smaller distance between the Sr2+ ions and the OH- ions in the grand lattice, making those attractions greater. And since those attractions are greater than in the Sr2+ lattice, that results in greater energy needed to break down those bonds. And since there's more energy needed to break down those bonds, that means there's a greater lattice energy, which explains the greater lattice energy in the Mg2+. So now I'll show you the answer, the written answer, and there we go. That is it.
Hey!
So now we're finally at the last question of the FRQ, and we need to calculate our G value for the reaction we chose, which is the one with the titrant of Cr2O72-. So using our equation for G, we have G equals negative N Faraday's constant, our E value. So plugging in all our numbers, first we have to look at N, so the number of moles. Now we have 6 electrons here, and we know that we need to flip this half reaction and multiply by 3. So the number of moles, which is based on the number of electrons in both half reactions, will be 6. So G equals -6 times Faraday's constant, which is just on your equation page, so don't worry about memorizing this number, is 96,485 times our E value, which is 0.63. And that equals -3.6 times 10 squared. And remember to always put your units when you can. So this is kilojoules per mole. Great. We're all done.
Sorry, Joanna.
She rides the night next to me. She leads me through moonlight, only to burn me with the sun.